Assalamualaikum warahmatullahi wabarakatuh. Good morning. I would like to present our research titled Characterization of A2G AV communication channels under Rician fading condition. With the screen. This research is collaborative effort between several colleagues from our institution, Adiono, Joko, Suryana, Fadjar, Rahino, Triputra, Asyaraf, Hidayat, Siti, Vivi, Octaviany, Yomi, Guno as the presenter for this session. This research is being presented for the Indonesian Journal of Electrical Engineering and Computer Science, paper ID 39020. Next slide, outline. This slide provides an overview of the structure of today's presentation. This presentation consists of 4 main sections. Background, I will explain the background of the research, specifically why it is essential to understand the characteristics of communication channel between UAV and ground station, particularly under Rician fading condition. Method, I will present the methodology in this study, including the experimental approach, parameter, and the process data analysis and processing. Result investigation. The result investigation section, I will present the key finding of this research, focusing on the impact of the Rician factor on bit error rate, which was simulated using OFDM with QPSK modulation at a frequency of 1,800 MHz. Conclusion. Finally, I will conclude the presentation by summarizing the main finding of this study and offering several recommendations for our future research. Next slide, background, UAV lab communication link, current research. The diagram illustrates the communication link between the UAV or lab and the ground control station. The UAV is equipped with several subsystems, such as the OCC, which manages communication link, sensor, and avionics. All these components connect through communication channel to the GPS, or eye-to-ground point-to-point line of sight communication. UAV communication often face several challenges, such as path loss, shadowing, and multipath fading, which can lead to a degradation in signal quality. Next, we observe every visualization of the research area based on document index in Scopus from 2017 to 2024. Research on UAV A2G labs communication has not showing significant growth in recent years. This highlights the need for further research, particularly in A2G communication under fading condition. So this research contributes by empirically evaluating the impact of the Rician factor on UAV A2G PTP line of sight communication, which is one of the primary challenges in maintaining high quality UAV communication. Next slide. In this diagram, I will explain the focus of our ongoing research, specifically regarding the variation in altitude and flight radius in open area environment. Next, in table 1, a comparative analysis that compares our research with previous studies related to UAV and 2G communication. From this comparison, we can observe that the method employed in this study offer a more comprehensive approach, emphasizing the Rician distribution and performance parameters such as QPSK modulation and K-factor distribution analysis. And next slide, method, modeling approach, data acquisition and file configuration, the calculation of key factor value. In the slide, discusses various modeling approach used in the characterization of UAV communication channel with a particular focus on the empirical approach. In addition to empirical modeling, there are other approaches such as deterministic, stochastic, and geometry-based stochastic model. Each of these approaches has its own strengths and weakness, depending on the complexity of the environment and the dynamic of the observed UAV canal. In the table 2, we also present the A2G UAV parameters. This include the UAV pilots with concept of an SDR and a Raspberry Pi operating at a frequency of 1,800 MHz with a signal bandwidth of 2.5 MHz. The UAV was tested at 3 different altitudes and flight radius at 10 meter, 20 meter, and 30 meter, and the same parameter with flight radius. The devices used for data collection were Raspberry Pi 4 and SDR dalam Pluto. And next, explain the data acquisition process and flight configuration employed in this study. As illustrated in the following video, the UAV was tested at various altitude and flight radius configuration. The UAV was flown at 3 different altitudes, X1 10 meter, X2 20 meter, and X3 30 meter. At its altitude, the UAV executed circular flight with 3 different radius. Radius 1, 10 meter, radius 2, 20 meter, and radius 3, 3 meter. Additionally, the diagram here depicts the antenna configuration at a frequency of 1,800 MHz connected to the signal phone BB60C measurement device, which was used to capture and record signal data during the flight. In determining the key factor value, it is derived from the probability density function of the Rician distribution. The PDF formula, as shown in formula number 2, illustrates how the probability of the variable R is influenced by the parameter sigma and A, where R represents the received signal. To calculate the character from the measured data, we begin with the moment of the original Rician distribution as described in equation number 6, where n represents the moment order used in the calculation. In this analysis, we use the first and second order moment. The process of calculating the key vector can be determined through the ratio of the first moment to the square root of the second moment. As shown in equation 9, this ratio can be expressed as a function of the variable sigma and k. In the process, the hypergeometric function is utilized, which is then transformed into a Bessel function to simplify the calculation. This transformation results in the final form of the equation as indicated in equation 13. Based on the measurement data, we calculate the ratio between the first and second moment. By applying the matching function method expression system, we can accurately compute the K-factor value. The next result and discussion. In this slide, we will examine the histogram data using full text distribution generated from simulation at 1,800 megahertz. As we can observe, a higher K-factor value, key 16.3 at 10 meter and distance of 20 meter with angle of 27 degree result in a more centralized voltage distribution with lower variance. This indicates that the signal stability is enhanced, other scattering effects are minimal. Conversely, with a lower K-factor value such as K 2.39 at the same height of 10 meter, but at a closer distance of 10 meter and an angle of 45 degree, we observe a more dispersed distribution. This condition indicates an increase in multipath effect. From the data result, a higher K-factor contributes to better signal quality. And next, we observe a two-dimensional 2D visual representation of the K-factor distribution at the frequency of 1,800 megahertz. The graph illustrated the variation of K-factor values based on height and radius. The x-axis represents the radius meter, and while the y-axis indicates the flight meter. As seen in the graph, the darker the color, the higher the K-factor value represented, and then the lighter the color, the lower the K-factor value. In other words, the variation in the K-factor value with change in height and radius significantly impact the K-factor and the flight angle. And next, performance testing was conducted using the basic FDM scheme. We involve only the modulation, and the FFT and FFT process, and the transmitted and receiver side. The channel model user is Rician with fine K-factor combined with adaptive white Gaussian noise. The simulation was performed using MATLAB software by variable NR2 and NY2 were generated as Gaussian random variable with calculated mean and variance. Meanwhile, the Rician fading coefficient, Rician coef, is computed by taking the skew rate of the sum of the skew rate of the in-phase and quadrature components. This process involves modifying the input signal in channel by multiplying it with Rician coef to apply the Rician fading effect. Subsequently, the faded signal is further processed by adding Gaussian noise AWG based on this specified SNR, producing the output signal out channel. Undercut out channel use the compensate for the multipath effect induced by the Rician fading coefficient on the signal. And next, the simulation result indicates that a good performance is achieved with a K-factor of 16.3, where at SNR of 10 dB, the bit error rate decreases. This shows that signal with a high K-factor maintain good quality with minimal transmission errors. Poor performance is observed with a K-factor of 2.39, where even a high SNR of 30 dB, the bit error rate remains elevated. This suggests that under low K-factor condition, the channel is more susceptible to multipath interference and fading. Next, conclusion. In conclusion, the research investigates of the A2G point-to-point loss LOS communication channel using QPSK modulation at 1,000 and 800 megahertz. The relationship between bit error rate and signal noise ratio offering K-factor value the different flight configuration, including altitude, distance, and angle. The simulation analysis results solve high K-factor such as K 16.3 shows much better performance at an SNR of 10 dB compared to a lower K-factor such as K 2.59 at an SNR of 50 dB. This indicates the existence of multipath scattering effects. In future research, we propose to use a simulation technique that combines synchronization and equalization to improve the SNR quality using a more complex FDM method to describe real condition. Okay, the next slide is my reference. Okay, thank you. Thank you for your attention and time. Assalamualaikum warahmatullahi wabarakatuh.